Welcome to the Strength of Materials introduction. So before we get started, this is a basic introduction to the strength of materials. We'll be discussing the necessary terms which are ubiquitous in mechanical engineering disciplines. So this means if you're a mechanical or civil engineering student, you will meet this strength of material discipline everywhere because you are dealing with some sort of loaded structure. So you ought to optimize the usage of materials and choose the right material as well. So you need to prevent failure at any cost, or at least extend the lifetime of the product. So many notations vary from country to another or from language to another. So when using textbooks or online resources, please make sure to read the symbols associated with the terms. So sometimes you use capital letter, other books use like a certain Greek, some books also don't use Greek at all. So you just need to understand what the letters mean in each textbook. So even though most of them are standard. Well, this voiceover is going to use a modern Greek pronunciation for Greek letters and symbols. And all the units are metric, so this means Newton, millimeter, megapascal, Newton, millimeter, and so on. So let's get started. So the strength of materials or mechanics of materials is widely used in both mechanical and civil fields. Understanding the subject allows technicians and engineers to better analyze systems and to build more reliable products. Mechanisms are succumb to forces, torques, and loads, exposing them to deformation. The latter, which I mean deformation, should be thoroughly studied, since as we have already mentioned how the objects and beams that we are studying take part in a mechanism. Thus, every deformation counts. The slightest mistake in calculation or choice of either material or dimension can lead the system to fail. Reliable systems are demanded and essential for a sustainable future for the industry. So, we're going to start with our first terminology. And we have here this drawing of a normal stress. So if you're familiar with the phenomena of bending, tension, and compression, so you have this kind of normal force to the cross section. So we are associate these solicitations to a normal stress denoted sigma, which is a pressure whose direction is perpendicular to the cross-section of the beam, where sigma is equal to F over S, where sigma is a normal stress in Newton per millimeter squared or megapascal. So these are the same unit. The F, which is the force represented by these arrows, is the normal force applied to the cross-section in newtons. And S, which is this surface over here, is a cross-section area in millimeters squared. So note well that S can be also found as A. So you have the choice in here. So we have seen the normal stress, so we have here the shear stress. So torsion and shearing deal with shear stresses. Those are associated with a shear stress denoted by TAV, a pressure whose direction is tangent or parallel to the cross-section of the beam, where TAV equals F over S. So basically it's the same thing as the normal stress. So here we got TAV, the shear stress in Newton per millimeter squared or megapascal. F is the tangential or shear force applied to the cross-section in newtons. As you can see here, the force is within the plane and it's not perpendicular to it. And the S or A is the cross-section area in millimeters squared. So this is the Hooke's law, and it's really important. We are going to explain this graphic in detail, but let's just distinguish between these two things. You know the sigma, which is the strain stress or stress strain graph, which is sigma equals f of epsilon. And here is what you get. This is the graphic. So this is the strain on the x-axis, and the stress is on the y-axis. So the same thing goes for the shear stress, which is tau equals f of gamma. So you see here, on the x-axis we got gamma and tau in the y-axis. There is no problem with these two so far, so we're going to explain this in detail. So Hooke's law is basically something that you can extract. So E equals sigma over epsilon. So this is very important because this is called Young's modulus. And you know, there is another modulus you can extract from the shear forces as well. So you know, Coulomb's modulus, denoted G, is calculated as follows. It is tau over gamma. So Young's modulus represents the modulus of longitudinal elasticity, whereas Coulomb's modulus or shear modulus represents the modulus of transverse elasticity. So yeah, we'll carry on. So there's a relation between E and G, and it can be deduced from the phenomenon of the variation of the cross-sectional area as a result of length variation. A certain Poisson's coefficient, denoted nu, links both moduli through the formula G equals E over 2 times 1 plus nu. And what I'm talking about here is explained in these two obvious diagrams. So you see here, when something is solicited to tension, so two opposite forces, you see this is the initial beam, which is in yellow, and this is how it became, which is in red. So you see how the cross section is like diminished, and you see how the length has increased. So you see here what I mean. This is it. Same thing in compression. So you see how the cross section is increased, but the length has decreased. So yeah, we got the Poisson's ratio, which is a relation between lateral strain and axial strain as well. So nu equals minus epsilon of the transverse over epsilon of the axial. And there is a little thing here, so you know that why we add the minus sign is because there is one that is going to be reduced, like in this case of the tension, we got the reduction in the cross-sectional area. So we got here a negative strain, and here we got a positive strain because it's increasing in length, which is the completely opposite case in compression. So you won't really get a negative value, so we would add a minus. Fast forward to the tensile test. So it is an application of a tensile load to a specimen that will keep getting stretched until reaching a maximum elongation, and that's when the specimen eventually fails and breaks in two parts. So note, while I'm saying two parts, not two halves, because it all depends on the microstructure of the tensile specimen. So this is an example of the tensile specimen. This is a screenshot from a tensile test I made in Abacus. No, it's in ANSYS. I'm sorry for that. So note well, the rupture might happen in the middle, as it can happen here or anywhere. So you have to consider where the most vulnerable point is in the specimen. So the test aims at determining some mechanical characteristics of the studied material. So we got here a tensile test is used to literally determine these mechanical characteristics by using a device that continually records the evolution of the load and elongation. So the elongation, not to be confused with strain, are quite different but are related, and I'll show you how they are related. So this is a force displacement diagram is drawn as follows. So you see here, this is the force displacement diagram. Note well how it has three notable parts. So from OA it's almost linear, and then from A to B it somewhat stabilizes, and then we got here a nonlinear part which is like a curve having a maximum, and then it just has a rupture point in here. So these are the same parts that remain for the next and more important graph. So we got here the Fe is what you say the force where the elasticity limit is denoted in here. So this is the last elastic point, and for here it's like we're starting to have a plastic behavior, and then we got here a maximum force, and then we got here the rupture. So this is where the specimen breaks off. So we're going to explain this right away. So this is what I'm talking about. This is the stress strain or strain stress diagram, and it's, as you see, almost the same as the previous diagram. So you have here the sigma E, which is the marking the last elastic point, sigma M, which is the maximum stress, and sigma R is where the specimen or the part is having a failure, so it breaks in here in this point. So we can just relate to these two graphs or diagrams, if you wish, with these formulae. So tensile strength is denoted sigma M, where sigma M is F maximum divided by S0, which is the initial cross-section area. And the rupture strength is denoted sigma R, where sigma R is Fr over S0. Elasticity limit is denoted sigma E, where sigma E is Fe over S0, and finally the elongation is denoted epsilon, where epsilon is the delta L over L0, and delta L is just the L ultimate, so here the last elongation minus the L0. So this is what delta L is. So now we're going to talk in a very detailed way about these three zones in here. So why are they here and what are they for? So we're starting with the green zone in here, which is OA, and it represents a linear variation of the stress. Here stress and strain are proportional. This makes it sigma is equal to F of epsilon, where this function F of epsilon is like sigma is equal to a number A times epsilon, and that's all. And give us the relation. So E, Young's modulus, equal to sigma over epsilon, where E is Young's modulus or the modulus of longitudinal elasticity. The zone is limited by the elasticity limit sigma E. So here is where sigma E is. And this is the last elastic point in the curve. So the zone AB represents the yield plateau. So you see it's almost stable. So it is when the tested specimen endures an increase in strain with a slight or no increase at all of stress, the material starts behaving plastically. So here we get an additional elongation, but the stress is not increasing or changing at all. And finally, the zone BC corresponds to the hardening zone, where both strain and stress grow until reaching a maximum value of stress sigma m, then a lower value of rupture strength sigma r, and a maximum elongation epsilon. So after reaching the sigma m, you get here a lower value of stress denoted sigma r, and that's where the failure or rupture occurs. So there's a phenomenon called necking. So let's suppose this is a specimen. In this case, you can see how the necking occurs. It's the heavy diminution of the cross-section area of the specimen due to the uniformity in the distribution of the strength along its length. So you see here, this is where the necking occurs. It's after the sigma m and before the sigma r. This is where you start noticing this phenomenon. If like the cross section here just keeps diminishing, it can reach the point, well, depending on the material, sometimes it can just become almost zero and then it breaks. Sometimes it just breaks before doing that. So depending on the material, you just have to see how that happens. Well, whether a simulation or you've seen the test in real life, it really does depend on the material actually. So this is all for this introduction. So thank you for your attention, and I hope you understood these basic information. So thank you very much for watching.